Hi, Trigoners. These are notes 4.1. Our objectives are to be able to determine the end behavior of polynomial functions of even and odd degree, be able to find zeros using long division and synthetic division, and be able to use the remainder theorem. So we already had a video on long division. We're going to start by talking about graphs of polynomial functions. So go ahead and pause the video and read the blue box and go ahead and learn about polynomial functions. So we already talked about what it means to be a polynomial. Let's consider first a linear function. So if we draw a graph of a line, you could think about a lot of things. You could think about its end behavior. Notice as x approaches infinity, so as x is getting larger, the y value, the f of x, is also approaching infinity. As x approaches negative infinity, it's getting smaller and smaller. The y value, the f of x, is approaching negative infinity. Also consider, let's consider a quadratic function. Let's say we have something like this going on. Notice that as x approaches infinity, the y value, f of x, approaches infinity. As x approaches negative infinity, the y value, f of x, approaches negative infinity. So again, I'm looking at the ends of the graph. You could also think about intercepts. Notice that this particular quadratic function has two x-intercepts. This linear function has one x-intercept. You also could have graphed a quadratic that perhaps looks something like this, where we have no x-intercepts at all. You could have graphed a quadratic that looks something like this, where perhaps it has one x-intercept. Let's see, what else could we think about? You also might want to think about the degree. Notice that the line had an odd degree, because when you write an equation of a line, for example, you might say y equals x plus 2. So the degree is odd. We talked about degree a little bit. Also, you might want to think about a quadratic. You might have a quadratic that looks something like, I don't know, something like the quantity x plus 1 and x minus 1. That would work for this particular quadratic. And notice that it would be y equals x squared minus 1. And that would have an even degree. Next, we might want to talk about turning points. So a point on a continuous graph that separates an increasing portion from a decreasing portion, or vice versa, is called a turning point. So for example, a parabola, this graph right here, a different color, let's see. So this graph right here, this has one turning point. Notice there's one turning point where it's decreasing, now it's increasing. Increasing, now it's a linear function, does not have any turning point. So that's interesting. So it was a quadratic, and the degree was 2, and it had one turning point. Okay, interesting. All right, so let's go ahead and look at some of these other things. So it says the properties of graphs of polynomial functions right here. Go ahead and pause the video and read about the different properties of polynomial functions. We're also going to be talking about zeros or roots. And notice over here we had this example where I said, for example here, we had two x-intercepts, one at x equals 1, one at x equals negative 1. Those are zeros or roots, x-intercepts. And notice because, for example, x equals 1 and x equals negative 1, there we go. Those were zeros of the function. So the zeros are the solutions when p of x equals 0. If the coefficients of p of x are real, so if some polynomial, the real zeros are the x-intercepts, just like this example right here, where we had 1 and negative 1 were the x-intercepts. I'll highlight it for this example right here. Okay. However, let's go back to the other example. If you consider r of x, or let's see, what do we call it? Oh, right here, r of x. First of all, if you set r of x equal to 0, notice that our zeros are at plus or minus 2i. So what would the graph look like? Go ahead and pause the video and think about how you would graph that. How to graph that, if you go ahead and expand, we know that we have x squared minus 2xi plus 2xi minus 4i squared, and I squared is negative 1, so we have x squared plus 4. So notice this is a parabola moved up 4. We know all about transformations. So notice there are no x-intercepts at all. So notice that we had no real zeros. We had two zeros that were plus or minus 2i, which was not a real zero. And notice we didn't have any x-intercepts. Very interesting. Okay, so let's take a look at these other graphs here. They are graphs of polynomial functions with degrees 1 through 6. What do you notice about the end behavior, turning points, zeros, etc.? So go ahead and pause the video and think about all of those things for each of those graphs. Okay, so for these first graphs, we had a linear. Notice we had degree 1. We had a cubic, degree was 3, and a quintic, a fifth degree was 5. And notice those were odd degrees. And look at the end behavior. As x approaches infinity, so as x is getting larger, the y value is approaching infinity. As x approaches negative infinity, the y value approaches negative infinity for all of these odd degree functions. So also take a look at the even degree function. So this was the parabola. This was a degree of 2. We had a degree, a fourth degree, and degree 6. So that was an even degree. And look at this, the end behavior. As x is approaching infinity, the y value is approaching infinity. As x is approaching negative infinity, the y value is approaching positive infinity. So for all of the even degree functions that had that same end behavior. Let's take a look at turning points. So notice this was degree 1, no turning points. This was degree 3, 1, 2, 2 turning points. This was degree 5 and it had 1, 2, 3, 4 turning points. For a parabola that was degree 2, it had 1 turning point. And this was a fourth degree. It had 1, 2, 3 turning points. Degree 6, 1, 2, 3, 4, 5 turning points. Something about turning points that's interesting though. If you grab your calculator right now and if you graph y equals x cubed, it'll look something like this. So notice it was a cubic, but notice it actually didn't have any turning points. So when I say turning points, notice that you have at most one less turning point than the degree of the function. So for example, if I looked at something like this, and if I covered this up and I said, could this be cubic? You would say, well, no, because a cubic could have at most 2 turning points, one less than the degree. And this had the degree of the function. This had 1, 2, 3, 4 turning points. So this has to be at least degree 5. Okay, very good. Turning points. And again, zeros. Notice this was degree 3. It had 1, 2, 3 zeros, 3 x-intercepts. This one was degree 5, 1, 2, 3, 4, 5. 5 x-intercepts. And again, we're going to talk about zeros a little bit more in just a minute. Actually, it might help if we think about a parabola, because I know we've spent a lot of time on parabolas. But again, if we have -1 and 2 are x-intercepts, wouldn't the equation look like this? Wouldn't it look like the quantity x plus 1 times the quantity x plus 2 minus 2? So again, these are x-intercepts. These are real zeros. Okay. Great. Let's go back to this cubic here. So notice this, if I just grab my calculator and type in y equals x cubed, it is degree 3, but notice it has 1 x-intercept. Very interesting. So again, I'm thinking that if it's degree 3, there are at most 3 real zeros. Okay, let's keep kind of taking a look at all these different types of graphs. For number 4, I would like you to just list the zeros. Look at the graph and tell me what the zeros would be. Go ahead and pause the video and write down the zeros for 4a and b. Here we go. So the x-intercepts are zeros of the function. Nice job. What we're going to do now is we're going to consider a graph. So if I wanted to graph f of x, we've done this before. We knew that the x-intercepts were 0 and 1. And we could sketch a graph pretty quickly. But what would g of x look like? Pause the video and consider g of x. Hopefully you were able to consider transformations and realize that g of x was just f of x reflected over the x-axis. Okay, so when we graph, we have to consider that. For example, if we have y equals x squared, my parabola opens up. If we have y equals -x squared, my parabola opens down. So again, those are transformations. So what we're going to do right now is think about even and odd multiplicities. So if you grab, well, we'll grab our calculator for in a second, but we actually know what this looks like because we know that this is a transformation of our parent function. It's moved right to. Okay, so notice what happens when you get to the 2. We'll go ahead and pause the video and let's put part B in our calculator and see what happens. All right, I'm going to go ahead and do a zoom 6. Let's see what this one looks like. Oh, very interesting. Okay, so notice this particular graph. It looks like at 2 and 4 we had x-intercepts. Those are zeros. But look what happened. Get the calculator back. At 2, notice it passed, and at 4, notice it bounced. Or we could say it crossed the x-axis, and at 4, it is tangent to the x-axis. So it or touches the x-axis. But again, I like to say bounce and pass. So that's very interesting. So notice we had an even multiplicity where we had x equals 4 with multiplicity 2. We had an odd multiplicity, x equals 2, multiplicity 3. And again, you could pause the video and experiment with your calculator. When we have an even multiplicity, our graph is going to bounce. And when we have an odd multiplicity, it's going to pass. Okay, so we learned so many things. So what we're going to do right now is we're going to try and put all of the things that we just learned to use. And we're going to try and graph all of these graphs without a calculator. Let's see if we can do it. Okay, so first of all, I like to call this bounce pass graphing. Okay, and the first thing you're going to do is to consider the degree to get the end behavior. So for number 1, if I multiply this out, which I certainly would not want to do, but I would end up with like y equals x cubed and then, you know, a bunch of other things. So notice this is x to the 1, this is x squared. So since the degree is 3 and it's positive x cubed, it's not reflected over the x-axis, I know that the ends of my graph go in opposite directions. They look like this. Okay, the next thing I would do is find the zeros or the x-intercepts. So notice I have a 0 at -1, I have a 0 at 2. So these are the only places, because again, these are the zeros. These are the only places that your graph can touch the x-axis. The next thing you want to do is to consider, the multiplicities. Okay, so here goes, my friends. We are going to graph. We read a function like we read a book from left to right. So we're going to start at the left. When we come up to the -1, notice it has an odd multiplicity, so we're going to pass. When we get to the when we get to the +2, it has an even multiplicity, so it's going to bounce. Check it on your calculator. That's a pretty good sketch. It looks something like that. Go ahead and pause the video and try part B. Right, so part B, if I multiply this out, which I'm not going to, notice I would have x times x times x times x times x times x. I would have 6 x's. So notice there's a negative sign, so it would be -x to the 6th. I don't really care about any of the numbers right now. I'm looking for the degree. So notice it's an even degree, so the arrows both point the same way, and it's negative. That's reflected over the x-axis. So my end behavior looks like this. Okay, check. The next thing I do is find the zeros. I'll have a 0 at 0, 3, and if the factor is 2x plus 1, the 0 is -1/2. Oops, -1/2. So the only place my graph can touch the x-axis is at 0, 3, and -1/2. Okay, so now we read a function like we read a book from left to right. So you start at the left, and when you get to the -1/2, you are going to pass because it's an odd multiplicity. When you get to the 0, you are going to bounce because it's an even multiplicity. When you get to the 3, you're going to pass. It's an odd multiplicity. And again, check this on your calculator. That's a pretty good sketch. Nice job, everybody. Okay, let's go ahead and try the next one. Go ahead and pause the video and try part C. this might be a little confusing. Notice we have 1 minus x, quantity squared. You might want to think of this as negative x, or sorry, the opposite of x minus 1, then that whole thing squared. That might help you, because now you could think of negative 1 as squared. So when I multiply this all out, I'm not going to, but if I did, it would be x to the 4th. It would be positive x to the 4th, because again, negative squared is positive. So that's going to help me get my end behavior. The degree is 4, so my end behavior looks like this. Check. Next to the zeros, I have a 0 at 1 and 2 and negative 4/3. So those are the only places my graph is going to touch the x-axis. Next, we're going to consider the multiplicity. So just like we read a function, or sorry, a book from left to right, we read a function from left to right. So at negative 4/3, notice that the multiplicity is 1, so I pass. At, what comes next? At 1, my multiplicity is even, because it has a multiplicity of 2, so it has to bounce. At 2, it's an odd multiplicity, so it passes. Ta-da! Looks something like that. Okay, let's try the next one together. Notice if you wanted to, you could write this as the quantity x minus 2, right, with a negative. I pulled out the negative, but negative to the 5th power is negative. So if I multiplied this all out, it would be negative x to the 5th. And again, we don't really care about the numbers right now. We're just trying to get the degree. So I know that my end behavior looks like this, because if it's an odd degree, the arrows are going opposite ways, but this is negative, reflected over the x-axis. So I have 1, 0. Actually, I might want to, this is going to look kind of bad. I'm going to fix that a little bit. It looks something like this. Okay, so notice that there's 1, 0 at 2. So when I get to the 2, I'm going to pass. Now, again, this is a sketch, so you might make yours look a little kind of almost linear, but really it's going to have a little bit of curve to it. You could check it on your calculator if you want. But again, this is just a sketch, so I think that looks pretty good. Okay, so there you go. So the rest of the notes, we have one more thing to talk about, and that's synthetic division, and we are going to talk about that in class. Nice job, everybody.